Hey, what's up, YouTube? We're live. Welcome back. This is week 2, relearning number theory as a adult hobbyist, I suppose. So today I wanted to answer a couple of comments and questions from folks. Thank you to those who have written in. So I wanted to answer a couple of Q&As, and then the big thing that I wanted to do today is I wanted to set the roadmap of what is the goal of this series. I'm a very goal-oriented person. I want to know where we are headed before we even really start. And so the first few videos on my channel were number theory because it's where my heart lies. I love number theory. I think it's really just the most beautiful form of mathematics. And it's a great place for me to practice again and practice proofs because you really can't study number theory without proofs, I feel. So the first 3 videos were a little less structured, a little more like figuring out what I want to do with this channel. And then over the last couple of weeks, sorry, cat, hey, Luna. Over the last couple of weeks, we've done a week each in in linear algebra, and then a week in calculus. And so now that we're coming back to number theory, that's what I'm imagining. 1 week number theory, 1 week linear algebra, 1 week calculus. Now that we're back here, I've got a little bit more structure and idea of how I want to structure this entire practice stream. So once again, yes, this is a practice stream. My name is John, and yeah, this is, it's going to be a little rough around the edges here and there. It's not going to be a polished, beautiful, incredible masterpiece of a video like 3 Blue, 1 Brown or something, or any of those other amazing math YouTubers. But I hope that we can have some fun anyways, just along the way, and you can follow along in this journey as I relearn mathematics for fun this time around. So, first off, 2 questions. One, handle, at least in Discord, is HT. Welcome, HT. Thank you, friend of the channel. He asked in Discord, what did you do after your math degree? And let me actually get the actual phrasing. He said, I'm mostly focused on statistics. I'm doing a 2nd year doing maths at uni. I will have abstract algebra next semester and real analysis the semester after that. I'm also doing CS because I do want to have a job after graduating. And then he said, a bit curious, what did you do after you got your degree? Great question. So I am statistically like everybody else who studies math. I went into programming. So I did my 4-year math degree, and then I realized, oh my God, I'm not cut out for pure math right now. Or at least I didn't want to do it. I didn't want to do graduate school. And it's because at the same time the iPhone was coming out, and I was a huge Apple fanboy, even before the iPhone. And I was like, I want to learn to program. I want to get a job. Just like you, I want to get a job. I don't just want to study math for fun. And if you don't go to grad school and get a PhD, it's pretty hard to make a major career out of mathematics in and of itself, I think. You can teach high school, and that's an awesome path in life, and I really strongly considered that. But no, I fell in love with iPhone programming, and so I learned to build apps. I worked at a couple of companies. I worked at one company in my small town, and then just through crazy coincidence of, a friend of a friend connected me with a recruiter at Apple, and then I got to work at my dream company. I worked in Silicon Valley. I worked on iMessage at Apple, and then after that I worked on payments at Lyft, the payment systems. After that I worked as an iOS engineer at Google. And some people who have been watching these videos know that I've got a lot of free time right now to relearn math because my entire team, my entire organization got laid off at Google. So here I am. Now I've got a lot of free time. I'm a little bit bored and jaded about iPhone programming nowadays. It's not like it was 15 years ago where everybody was so excited, like there's an app for that, like this thing is changing the world. All of a sudden I can have a flashlight on me at all times, like at a moment's notice. Like just think of how simple that was. Like that changed the world, just that you could have a flashlight. Like that's cool. That's cool as hell. And then obviously there were a million other things that the iPhone changed, like the fact that you could have a computer on you at a moment's notice. But yeah, nowadays people are a little bit more burnt out on apps, app fatigue, all that. Yeah, man's got hit by the tech layoffs. I did. But it's a dream come true. Like, I'm not complaining because the severance was very good. Like, that's not secret information. You can see the blog post. Severance was very good. So I am not complaining. I get to, in a sense, be paid to relearn mathematics right now. So I'm on sabbatical, and for personal reasons, it just makes sense for me to take a little bit more time off. I'm not retired. I am not early retired by any means. I'm going to go back to a job at the right time. But right now, I just want to rebuild my love and deep hobby in mathematics. Yeah, thank you. Thanks, Leo Lectures. Also, good to see you, Leo Lectures. Thanks for tuning in. Pretty similar to you, HT, I think. I studied computer science. I learned to program. I fell in love with it. I got really good at it. So I hope that you don't lose your passion and love of mathematics. If you're about to take abstract algebra and real analysis, obviously you must love mathematics to some degree. Also, if you're like signing up for the Discord of this weird, sloppy practice stream. Yeah, all right. And then second question was from friend of the channel, Anas. I mentioned Anas a couple of videos ago. He emailed me alongside Richard Borchards and somebody else asking for a mentor. And I was like, Anas, okay, as your new mentor, do not put Richard Borchards number 3 in a list of recipients. Richard Borchards, you send him an email by himself. You do not let him know that he's number 3 compared to this brand new YouTube channel and this other great one. But anyways, yeah, so Anas found 3 YouTubers. Richard Borchards, I forgot to mention it the other day. He has an amazing YouTube, and I feel like in a lot of ways I'm taking inspiration from his YouTube channel. I love his YouTube. He literally just uploads his lectures for UC Berkeley math students. Like the Intro to Number Theory lecture series is incredible, and it's just got his face on the side, and he's like doing math, on a projector or like, with a camera on paper on the left. So yeah, thank you, Professor Borchards. For those who don't know, Professor Borchards is essentially a Nobel Prize winner in mathematics. It's the Fields Medal. It's slightly different, but it's the closest thing that math has to a Nobel Prize. And where was I going with all this? Yeah, he proved something amazing called the monstrous moonshine conjecture, which just has such a wonderful, romantic, delightful name to it. And someday I'd love to understand his work. So, but I don't know. My brain's too small to understand that kind of math for now. All right, so the question was, where to start with combinatorics? I'm not the person to ask. I haven't taken a combinatorics class. I haven't really dove deep into combinatorics, but you do learn a lot of it along the way, both in mathematics and in computer science. So, Anas, I think that you mentioned that you're interested in linear algebra for the sake of machine learning. I think that you will learn discrete mathematics if you do take a CS route, or if you want to learn artificial intelligence, you'll want to learn discrete mathematics, and that will include some combinatorics. Number theory isn't really combinatorics, but the two aren't that far apart, I feel. Combinatorics, for those who don't know, is the study of counting. So we have proved a couple of really cool combinatorial things, or I've shown a couple of things in this channel. I mean, I would say, this is what I said in my email. Start out with Pascal's triangle, understand Pascal's triangle, understand how it relates to counting items in the real world. Like if you want to take 4 pencils home out of 10, learn how that relates to Pascal's triangle. Then learn mathematical induction and other proof-based techniques. Mathematical induction will be very important in combinatorics and understanding counting. I do have a book on graph theory back there somewhere. Yeah, it's right here. I'd love to get into this because I think that graph theory and like a lot of combinatorial things in computer science, this is kind of super similar and related to combinatorics, I think. You probably also want to start studying statistics because that is where combinatorics is so handy and useful. Like if you want to learn machine learning, you want to learn linear algebra and statistics. That is your bread and butter. That's what's going to get you that fancy Google job. You want to learn linear algebra and statistics, and by just studying those two things, I think that you'll learn combinatorics along the way. That's my opinion. And if you do want to follow along with this channel, and if you want to get into combinatorics for its own sake, you're going to want to learn proofs, and we'll be doing that in this series, I think. Hey, Leo Lectures and Ben, you're both here, the grad students who actually know way more math than me. Nice, man. Borchards is great, isn't he? Like, his YouTube channel is a gem. It's like a real gem amongst like a wasteland of YouTube videos. I'm also kind of a Borchards mimic. Heck yeah, let's all be like Borchards, what's the word? Mimics, disciples, like like people influenced by Borchards. Amazing channel. Alright, so combinatorics is less prereq bound, so really any intro should be fine. I agree. Yeah. You don't need to know something like abstract algebra or number theory or anything before combinatorics. So you can, I don't know the book to recommend, but if you Google it, I bet that you'll find a lot of recommendations for a good intro to combinatorics book. Alright, so that was a lot of talking. That was a little longer than I wanted, but we got through our 2 Q&As. Let's pull up the iPad. Where the hell is it? Ah, here we go. All right, so we got the iPad up. Week 2, relearning number theory for fun. Q&A, done. We did those 2 questions. And also, to the viewer, I see that some people are watching these after the fact, which makes me very happy. Drop a comment below. I'll answer it at the beginning of the video. All right, so today I want to talk about what is the goal? Like, why are we studying number theory? Why did I choose this out of all of the various options of mathematics to practice for fun? Again, I am the math hobbyist. I'm doing this for fun. I'm not trying to go to grad school. I'm not trying to get a research position in math. I want to study this stuff for fun as a recreational math person. But why number theory? Really, the big motivation is this far-term goal for Maud's last theorem. So y'all see it all the time in my little channel avatar. I want to understand this because it is beautiful. I think it has fascinated lots of people. Um, it has captured the hearts and minds of so many people, this simple equation. It's something that I can show to a middle schooler. Like, everybody learns in middle school the Pythagorean theorem, right? That this has infinitely many solutions, like 3, 4, 5 in integers, that is. I forget the others. Doesn't matter. What is it? 11, 12, 15? Something like that? I forget. Doesn't matter. It has infinitely many solutions with integers, but there is no equivalent set of integers that solves the cubic version or the quartic version or any number n. Anytime that n is greater than 2, there's never, anytime that n is greater than 2, there is never an integer set of solutions to any equivalent sum of cubes, sum of quartiles or whatever, etc. Yeah, so that's pretty fascinating. I want to understand Fermat's last theorem. Like, that is the long-term goal. I don't know if we'll ever get there. I don't know. Maybe if I don't drop this hobby, like, in an ADHD way of just like, I love this hobby for 1 year. Okay, wait, no, I'm gonna jump to this other hobby. I think math as a hobby is going to be here for life for me. I want to build this as a deep, lifelong hobby. So maybe I think we can get there. I think grad students can get there nowadays, and I think we can get to grad student level math. I think, but that's a long-term goal. In the near term, I just want to get those muscles going again. Exercises, proofs. I want to be able to do a math proof again. It's been a while. I'm very rusty. 15 years ago, I studied math and I was decently good. I could have gone to grad school. But yeah, like, I'm sorry to burst your bubble. You don't do complicated proofs in the real world, unfortunately. As much as I wish you could get paid to prove that some space is compact or whatever, like, unfortunately, you don't get to do pure math in the real world. At least in iOS programming, you don't. I shouldn't speak for every field. So I just want to practice. I just want to get math back in my fingers. So that's the near term, and so much of the stream is motivated by actually solving exercises and doing proofs. Medium-term goal. What's a medium-term goal? This is where I want to focus today. I want to talk about some of the results. Like, what are we working toward? Like, some beautiful mathematics. I want to understand quadratic reciprocity. I sort of understood it in undergrad. I worked on a proof. I worked on understanding and being able to summarize and relay Gauss's proof using, like, the cyclomatic integers or something, the cyclomatic field, finite field of complex numbers or something like that. But I didn't feel like I understood why it's beautiful. I don't feel like I really completely grasped that. Yeah, I just want to take another go at it, because an amazing mathematician that I took courses from and did some undergrad research with, he said that in the class, the rest of the class wasn't able to get to quadratic reciprocity, but he said, if you have some free time this winter break, like, study this chapter. Like for a lot of mathematicians, it is like visiting the Louvre and seeing the Mona Lisa. For a lot of mathematicians, this is one of the most beautiful results in math. It certainly delighted Gauss. He proved it 6 times, 6 different ways in his life. And I think I've heard that quadratic reciprocity is one of the most frequently proved theorems in math. There are like hundreds of proofs of it or something. So I just don't think I got it. I don't feel like I completely got it. So that's like a goal that we want to work toward. Another one that I didn't even know when I was an undergrad. This one is gorgeous. Like, I love showing this to kids. I love showing this to like second graders that I'm working with. Like the odd versus distinct partitions of a number. And that's also older math. That's Euler. So, I mean, both of these are like, what, 19th century, 18th and 19th century math? This is fairly old stuff. Fermat's last theorem is new. This is complicated math. I mean, even more complicated, 1995. So it's going to take longer to get there. But yeah. All right, so let me see. Leo lectures, if one simple fact was different, Fermat's last theorem would be very simple to prove. I think I learned that in my abstract algebra class. I think it was something like the union of two things is not the thing. I don't remember what it is. It's like some common mistake that that undergrads make, or it's like a common counterexample. You probably know what I'm referring to. I wonder if I'm thinking the same thing. There's like some sort of common mistake. Like, you think that the union of two objects it's the same type of object, but it's not true. Or maybe the intersection. But, I remember my lecturer, my professor, he said that it's commonly speculated that that's what Fermat was thinking when he had a simple proof that he couldn't fit in the margins. That he thought that the intersection of these two objects was the same algebraic object, and he was trying to prove it but wasn't able to fit it, and then just claimed, okay, well, I'm pretty sure I know how this proof works, and then turns out he was wrong. Was thinking of doing a video on what if these big theorems were easy by talking about the little technical things that if different would change everything. Yeah, that sounds like a cool video. That sounds great. To be honest, I don't really remember what is up with quadratic reciprocity. Yeah, it's like something about relating squares modulo 2 different primes or something like that. It's something beautiful about how you can relate 2 different primes and like something called the Legendre symbol. I don't know. So, to that point, let's just get started. I want to work toward today. We're going to jump right into it. And you know what? I don't have to understand it, but I can at least copy it down. Let's write down quadratic reciprocity so that everybody is on equal foot and none of us understand what I'm writing down, and then I'm going to work backward. So, join me for this. A lot of people think that this is the Mona Lisa, or one of the Mona Lisas in math, one of the masterpieces. So, I love this book so far. This is a great book. Go get it. Andrew's Number Theory. In this book, it is... Where is it? Residue systems, linear congruences, Chinese remainder theorem, arithmetic functions. Oh, it's way before all of these things, isn't it? Primitive roots, quadratic congruences. Okay, quadratic residues. Here we go, actually. I was wrong. Quadratic reciprocity law. Yeah. Yeah, this is lovely. Let me read this intro out loud. The Quadratic Reciprocity Law, Chapter 9, Section 3. In this section, we shall prove a famous theorem of Gauss, the Quadratic Reciprocity Law, which enables us... Here, let me write this down. Quadratic Reciprocity Law. We're taking this from Andrew's section chapter 9, section 3. It's theorem 9.3. Okay. This is supposedly a masterpiece. And we will learn a little bit about it right now. In this section, we shall prove a famous theorem of Gauss, the Quadratic Reciprocity Law, which enables us to solve almost all quadratic congruences. This is not an easy theorem. Great mathematicians such as Leonard Euler and A. Legendre were baffled by it. It is some measure of the greatness of Gauss that he proved it when he was only 19 years old. Because this theorem is of fundamental importance in number theory, Gauss returned to study it many times throughout his life, and he gave at least 6 different proofs. That's pretty cool. And then there's a little footnote that says that this theorem has occupied the attention of many mathematicians is amply borne out, although slightly exaggerated, in the title of an article by Gerstenhaber, the 152nd proof of the law of quadratic reciprocity, American Mathematical Monthly, blah, blah, blah. Okay, so our first goal, however, is to prove a preliminary theorem called Gauss's lemma, ... I'm going to skip that, and we are just going to write down... Gotta head out, but have fun. Yeah, thanks, man. Thanks for stopping by. Not totally sure what you were talking about, but it could be another way to do it. It might have been that Z omega is a unique factorization domain for all roots of unity. No, that's not it. That's not it. Yeah, there's something else. But it sounds cool. I would love to see that video, Leo. Like, if you make it, that sounds like a really cool video. All right, so I can at least just write this down. I don't need to fully understand it. We can, every time that I write this down, I want to understand it a little bit better. Let GCD of two numbers m and p equal 1, where p is an odd prime, and let mu be the number of integers in the set m to m 1/2 p minus 1 m, whose least residues modulo p are negative. Then, here's the result. The Legendre symbol m over p equals -1 to the mu. Okay. All right. I did not understand that. Let's write it down. So what, again, that was chapter 9. I didn't understand that either. Don't worry. don't worry. If you are a random person following along out of curiosity, don't worry, I also didn't understand that. Oh, wait. Oh, no, this is Gauss's lemma. My bad. I was like, this doesn't sound familiar. Alright, so, shoot. Take two. Gauss's lemma. Alright, so we need that in order to get the Mona Lisa. Take two. Theorem 9-4. This is page 120 of Andrew's book. All right, here we go. Yeah, I was like, I do not see how this is related. The prior thing is equivalent to what I remember. If P and Q are distinct odd primes, then P, the Legendre symbol P over Q equals the Legendre symbol Q over P unless P is congruent to Q, which is congruent to 3 mod 4. Ha! That is actually very cool. Like, what? In which case... in which case, P over Q does not equal Q over P. Well, duh, right? I mean, I don't understand why Q over P. I don't understand why Andrews felt it was necessary to emphasize that, because that's already implicit in the word unless, right? But anyways, I shouldn't criticize. Yeah, so supposedly this is a Mona Lisa. I don't know. It is quite striking to me, because we have two prime numbers, any two prime numbers, and we have some way to relate and connect those two prime numbers, which have, the primes are like these atoms of numbers, and they're just somewhat mysterious. I don't see any reason that two prime numbers should be related to one another directly like this. Like, I think that's quite striking. And then, like, why are any two prime numbers so connected to 3 and 2 squared, right? Like, that's cool. Is that where quadratic reciprocity comes from? Like, a quadratic equation is a square, is a polynomial with a square of square degree, right? Is that why it's called quadratic? And then reciprocity means, you know, in some sense, like forward and back. Like, if I do you a favor, then you do me a favor back, like trading tit for tat or something. And so the way that somehow you can, like, in whatever that means, flip the any two arbitrary prime numbers in this equation, that's kind of cool. Like, that is cool. I don't fully understand this. Especially because I don't know what the Legendre symbol is. I don't remember. But, ooh, I will check out that math YouTube. Thank you. Yeah, there's an infinite amount of good math YouTube videos out there, so, you know, yeah, you can really get lost in how much good content is out there on the internet. I wish that math YouTube existed when I did a degree. Like, when I studied pure mathematics, like 15 years ago, like, YouTube was, like, in the early days. There was, like, chocolate rain, and there was, like, double rainbows and things like that, but there wasn't, like, super awesome years and years of high quality, like super awesome lectures, and everybody's on it, and like amazing people like Borchards. So, good to see you again, MD Ahmed. How are you? All right, so that's how Andrews writes it down. Let's also write it down. And again, that was page 120. Let's check out what the tiny scary book. How does this tiny scary book treat it? What page is it on? Let's just start out with that. Quadratic reciprocity law. Page 7. Page 7. All right. So, my God. All right. Theorem 6 by Gauss, he writes. Literally, the statement is just L by P equals P by L times -1 raised to the epsilon L epsilon P. Whew! What? Okay, and then the proof is like 2 sentences. Oh, no, it's not. But it's... Yeah, okay, he does the lemmas, and then... He does 2 lemmas, and then says Theorem 6 is now immediate. Anyway, so this is Sayre. Page 7. As opposed to page 120 of Andrews. Hey, Stan Strong. Good to see you, man. How are you? All right. Yeah, Ben H. We're all, like, Borchards fanboys over here, right? We're all, like, Borchards stands. Whatever the kids are saying. All right. Long since I was here. Sorry I was preparing geometry. No worries, man. Good to see you again, though. How's it going, Stan Strong? So, we're kicking off number theory week 2. Quadratic reciprocity law. I'm running a little bit behind schedule, so next time I'll also write down quadratic reciprocity according to Rosin. So you can just tell this is a bigger book. It's a hardcover. Therefore, this is an easier book. According to the pattern that we're seeing again and again. I'm just curious, what page is it on? We can at least get that. Quadratic reciprocity law, 417. On page 417, we state the law of quadratic reciprocity. Yeah. And then this is the form I remember, because this is the book we used in my class. So, next time that we just do some rote memorization, we'll write it down. All right, so my books, good question. The books that we're using for number theory, I should have it in the description. Rosin Andrews. So these are the last names of the authors. And Sayre. Sayre has a few number theory books, so course in arithmetic. Yeah. So there you go. All right. Let's do more rote memorization today. I want to just write down as many theorems from Andrews as we can in the next hour because I have to go. I have a little guitar meetup in an hour, and let's just see how far we can get. We're not going to get to quadratic reciprocity this week, but I think by the end of the week, I want to see if we can get to the fundamental theorem of arithmetic. I think that would be good. Chapters 1 and 2. Goal, we'll see how far we get. I mean, that sounds nice. The fundamental theorem of arithmetic. This will be familiar to people, to anybody who's done any amount of math, like learning long division. No, I don't have any recommendations for IMO books, unfortunately. I'm not your guy. I'm not your guy. So today is going to be light on exercises. We're literally just going to be writing down theorems and trying to memorize things verbatim. Let's just get a little bit of math in our fingers. Theorem 1-1. The sum of the first n positive. We're going to skip all the proofs. This time around, we're just going to write down math facts. Positive integers is n times n plus 1 divided by 2. All right. Theorem 1-2. These are both used to illustrate and practice and learn mathematical induction. So I do know that these are math induction proofs. If x is any real number other than 1, then the sum of x to the j equals 1 from j equals 0 to n minus 1, which is also written explicitly like this. X to the n minus 1 over x minus 1. Okay. So apparently you can prove that by induction. Makes sense. Usually whenever you have like a sum, like a series where you add many terms, it's easy to add the next one to complete the inductive step. All right. Theorem 1-3. This is called basis representation theorem. Let k be any integer larger than 1. Then for each positive integer n, positive there exists a representation n equal a naught k to the s plus a, oops, my iPad is out of batteries. I can't believe I forgot that. I kept thinking, oh my gosh, iPad almost out of batteries. Don't forget to recharge it. Whoops. I knew it too. Like, I saw it and I thought about it. I just get so excited about mathematics, y'all. All right, here's a moment to chat while it comes back to life. How's it going? I could get a coffee. I could just hang out and chill. Yeah, I don't know geometry books for IMO. I did get this book though. It probably would be good for you. It's not expensive. It's a just where is it? Where's my book? Oh, here it is. Yeah. Write this down. I think that this would be a good book. I've like barely even looked at it at all. But yeah, I think that this would be good for competition math. Yeah. And it's cheap. It's like 15 exams or something. Ooh, you got your first exam tomorrow on statistical inference. Look at you. Like, are you doing like a Bayesian probability in that class? I didn't learn anything about Bayesian probability until I took like a machine learning MOOC like after college. And it seems like a really cool different way to do statistics and probability. I wish I took a probability class in college. I never did. It's very useful. That's what they say. Ben H., do you have any recommendations for Stan Strong in terms of geometry books? Or geometry, how to study geometry? Or the IMO in general? I never did any competition math other than the Putnam. I did the Putnam twice. This one is a frequentist one. So is that what it's called? Frequentist is the traditional way where you do combinatorics and count all the frequency of possibilities divided by the total number. That's like frequentist statistics, and as opposed to Bayesian. I just remember Bayesian, you try to like infer some like hidden variables or something. Like, I don't know, it was like super cool. It was a different mode. More of a probabilist. Haven't touched geometry in years. That's cool. Because I didn't even know. Like, I guess, are Markov systems and Markov chains like super closely related to probability? I guess so. Like, I've seen how they can be applied to probability scenarios like an unfair coin or something. But are they used like... Because this is the third thing that you're mentioning that you're good at and that you've studied: algebraic topology, Markov systems, and now probability. And so in my mind, I'm like trying to connect the dots. I know algebraic topology is separate from the others, but that's really cool. This one is more confidence intervals and hypothesis tests. Nice. I never studied anything like that. One of the theorems I find coolest is the Kramer-Rao lower bound. It gives a lower bound on the variance of unbiased estimators. It just feels so cool. That sounds cool. That sounds cool as hell. I don't know half those words. I mean, I do know some of it, but like, I don't know what an unbiased estimator is. I have a guess as to what that might be, but yeah, Markov chains are very probability, right? Like it's like a way to capture and write down and kind of like project probabilities and steps into the future or something in some sort of system. I really want to build up like a complex model and example of the probability that a project at Google fails, like go/headwinds is the slide deck. Yeah, there's this problem in large bottom up companies like Google called the slime mold problem, and it just leads. It's kind of like an unfair coin flip or something. There's just ever so slight probability that people aren't going to do their jobs. And then because it's a huge company, those probabilities compound in, I want to try to build that up as an example. I think it'd be very fun as a, as a long-running Markov system stream example. Similar to martingales, which are very cool as well. I've heard of martingales, and I don't know anything about martingales. I would love to learn. That just sounds cool. Like, what is a martingale? Yeah. All right, let's come back to it. So I was taking notes. We're relearning number theory for fun. iPad is back to life. We gotta connect to Air Server again, AirPlay. I think I know a guy in the probability group doing a PhD in something called the slime mold thing. No way! I would love to learn about his research. A slime mold problem. So, I mean, this is connected to slime molds, like in biology, like you have like a culture, and then they behave very erratically, like a Brownian motion or something. I don't know, like very chaotic system, like from a bottom up organizational way. But they can also lead into like really beautiful generative systems or something like that. Yeah, that sounds cool. That sounds cool. I just would love to see that applied to like industrial engineering or whatever that's called. All right, so let's we got the iPad back. If I double click the right thing, where is it? This one? Why are we... Oh, yeah, okay, good. All right, so we're back. Like the Chance of the Rapper song. Theorem 1-3. Where is it? Yeah, basis representation theorem. Let K be any number. There exists a representation. What happened? Now is the pencil dead also? What's going on here? No, the pencil's fine. Just disconnected. Alright, so this I'll reframe in a second. Then there exists a representation n equals a naught k to the s plus a1 k to the s minus 1 plus ... plus a s. And he marks this with equation number, where a naught is not equal to 0, and where each ai is non-negative and less than k. Furthermore, this representation of n is unique, it is called cool. All right, so Ben, tell me, am I the only one? Like, sometimes, like, when I'm trying to study a. Oh, okay, you got to head out. Well, good to see you, man. Thanks for stopping by. But if you see this in the future or whatever, do you just, like, write out theorems and then write out proofs and then try to, like, drill them and, like, memorize them in, like, a spaced repetition, Anki kind of way? Because that has been my method to learn a lot of math. All right, next we get to chapter. I'm going to go ahead and call out that we're switching to chapter 2, the fundamental theorem of arithmetic. So this is what we're trying to get to this week if we can. Chapter 2, Fundamental Theorem of Arithmetic. 2.1, Euclid's... I'll start calling out the chapter and section names. Why not? Then y'all can get a sense of how this book is organized. 2.1, Euclid's division lemma. Well, no. Damn it. Theorem 2.1. I don't like this. Theorem 2.1. Euclid's division lemma. I don't like that I just repeated the exact same thing twice. So we'll fix this in a second. For any integers k greater than 0 and j, for any integers k greater than 0 and j, there exist unique integers q and r such that 0 is less than or equal to r less than k, and j equals qk plus r. Okay, I remember this. So this is, like division. This is uniqueness of division, and the remainder. So if you've done any amount of math, like if you've done elementary school math, you've probably learned long division. And that's what you're doing is you're applying this division algorithm again and again. So this is saying that you can divide any number by... You can divide any number by another number, and then find a remainder. I don't know. I didn't state that great, but whatever. Let's keep going. Theorem. And I meant to say that this one, the basis representation theorem, is like saying that in base 10, the number 1, 2, 3, 4 is 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 plus 4. So the base is 10. But you can write down numbers in other bases as well. So you've probably heard that computers use base 2 as an example. Okay. Divisibility, definition, example. In the future, we will do all this stuff more carefully, and we will actually write down the proofs and try to memorize proofs, and then be able to state the proofs ourselves without memorization. But today we're just writing down theorems. If A and B are integers, not both 0, then the GCD of A and B exists and is unique. Do I want to write down corollaries? Yeah. Sometimes the corollary is the beautiful thing, and the theorem is the way to get to the beautiful thing, right? So let's write down corollaries. Corollary to 1. So it would be very good to have a mental map of how we get to various mathematical results. If D is the GCD of A and B, then there exist then there exist integers x and y such that ax plus by equals d. I do remember this one. It's really nice that you can express the GCD as a linear combination of two numbers. Yeah, that one's really lovely. And I remember seeing Euclid's proof of this that really stuck in my head in a great way. I'd love to show that soon. Corollary 2, whenever we get to that in this book. Corollary 2. In order That's lovely. And then we get to this nice one. Theorem 2-3. If A, B, and C are integers, where A and C, dang it, where A and C are relatively prime, and if C divides AB, then C divides B. Okay? A, B, and C are integers, A, C relatively prime. If C divides A, B, A and C... yeah, okay. That one makes sense to me. Corollary 2-3. If A and B are integers, P is a prime. P divides AB. And he writes this symbol, which I assume means P does not divide A. Then P divides B. I've seen this more often. Corollary. So we're just getting these things literally in muscle memory in our fingers, and reviewing, oh yeah, what is number theory? What kinds of theorems, results, what are we working toward? What are some of the mathematical facts that we want to get to? I don't know if we're going to get all the way to fundamental theorem of arithmetic in a week. This is a lot of stuff. I mean, we're not going to carefully get through all the proofs. Maybe I will, but maybe not on stream. I don't know. We'll see. Theorem 2-4. The linear Diophantine equation ax plus by equals c has a solution if and only if D divides C, where D is the GCD of A and B. Furthermore, if x naught y naught is a solution of this equation, then the set of solutions of the equation consists of all integer pairs x, y, where x is x naught plus tb over d. All right, so at this point I'm getting lost. I'm not remembering that much about this. I kind of remember this. And y equals y naught minus t a over d. T, he writes integers this way, which is weird. Why? Yeah, Andrews really just doesn't use like the Blackboard Z letter or whatnot very often. All right, and now here we go. We're getting there. Theorem 2-5 fundamental there's often like a fundamental theorem of blah blah blah. Like whenever you have a subject like calculus, number theory, algebra, usually there is like a fundamental theorem of calculus, fundamental theorem of algebra, fundamental theorem of arithmetic. So, if it has that kind of name, it's probably pretty important. For each integer n greater than 1, there exist primes p1, p2, all the way up to pr such that n equals okay, yeah, this makes sense. This factorization is unique. I like this way of writing it. I like this style. This is more elegant to me. This other book, Rosin, I remember it had like a lot of kind of complex notation, like n equals p1 alpha 1 p2 alpha 2 ... pn alpha n. And what in this one, p1 is less than p2, strictly less to pn. Whereas Andrews allows the inequalities to be less than or equal to. So in this case, this P1 can be 2, P2 can be 2, P3 can be 3, P4, like you can repeat the primes. So, yeah, I kind of like that better. It just looks nicer. They're both equivalent, but somehow that's a little bit nicer to me. And it's the same. It's the same thing. Theorem 2-5. And then we're done. After that, I doubt that Anas is still watching, but if he is, after that, chapter 3 is on combinatorial, and computational number theory. So like what I was saying earlier, that combinatorics is really closely related to computer science, meaning computation science. I wasn't completely wrong. Like here, combinatorics, computation. Yeah. So stay tuned for that. You might learn combinatorics in this channel a little bit. And I don't know other channels to recommend to you. But cool, that was fun. So we wrote down a lot of theorems, and here's our roadmap for this week. After that, I don't know if we can completely skip chapter 3. Yeah, oh no, there's nice stuff in here. Like Fermat's Little theorem. Yeah, you can't like have the goal of Fermat's last theorem without studying Fermat's Little theorem, right? We can't skip that. Yeah, chapter 4 is quadratic reciprocity, I think. Oh, no. Chapter 4 is fundamentals of congruences. Okay. Yeah, so chapter 4 is just congruences. Chapter 5 is solving congruences. Chinese remainder theorem, arithmetic functions, primitive roots, prime numbers, quadratic residues, distribution of quadratic residues, additivity, elementary partition theory. All right, so we already passed quadratic reciprocity. That's probably in quadratic residues chapter. Fun. Okay, I think I've lost everybody, but let's solve a problem. Andrews. I want to at least cross off one exercise. I think that this one is really lovely. Andrews 115. This is one that I want to keep in my memory because I had forgotten it. This is a lovely one. I'm going to try to keep this in my memory as sum of odds is square. Okay? Like, if you add the odd numbers, let's get this table. Let's see. I mean, this is how I like to show this sort of stuff to kids. When n is 1, what is 2 times n minus 1? Well, 2 minus 1 is 1. When n is 2, 4 minus 1 is 3. When n is 3, 6 minus 1 is 5. Okay, so we can see that this column is all of the odd numbers. And yeah, if you believe like some of the factorization or the division algorithm stuff and whatnot, like the theorems that we wrote down earlier, then that makes even more sense. Now, we're going to add all the odds. I'll write it like that. Sum odds. 1 plus... So what I'm going to do is I'm going to add this row to what was before it. So we only have one row so far. So it's just 1. But now 3 plus... These two added together, 1 and 3 adds to 4. What about 4 and 5? They add to 9. What about 9 and 7? They add to 16. What about 16 and 9? They add to 25, right? Well, guess what? That's exactly like n squared. 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. On and on, forever. Like, how do we know that this pattern always works? Is it only a coincidence? Because we've only checked 5 numbers so far. Can we prove that this formula is always true? If you add the first n odd numbers, the sum of odds is square. The sum of the first n odd numbers equals n squared. This is going to be a proof by induction, just like some of the ones that we've done in the past. We can see the equation holds for n equals 1. 1 equals 1 squared. Then assume it holds for some k greater than or equal to 1. We've already showed that it works for a few, so let's assume that k is like the most recent one we've checked. Like we've checked a few. Let k be the most recent one we've checked. Imagine that we did this 10 more times, then maybe k would be 15. But there's some most recent number that we've checked so far. We want to show it then holds for k plus 1. So the left, I wouldn't write it this way. The left-hand side of the equation is, I would say, thus 1 plus 3 plus 5 plus ... plus 2k minus 1. This would be if n was k plus 1, you would get the next term, the next odd number after 2k minus 1. By assumption, we assume again that it holds up to the kth odd number. Then we have n squared. Oh wait, no, sorry. Since we assumed that it holds for this first, we assumed that it holds for k numbers so far. And then we add the next one, 2k plus 1. Well, this is delightfully simple. This polynomial factors exactly as k plus 1 quantity squared. Therefore, the proposition okay, therefore the proposition holds for the next number, and so it holds for every number greater than or equal to 1. Because we showed that it works for 1, and then we showed that 1 implies that it works for 2, and then 2 implies that it works for 3, and 3 implies that it works for 4, on and on forever. So there's an exercise. That was Andrew's 115. Lovely. It is a delightful... I really like this book so far. Yeah, so I've already marked it off as something that I've done for myself, and maybe I'll do it again deeper to show that we did it on stream. All right. Thanks, everybody. I think I've lost most people. If you are still watching, thank you. Means a lot. Drop a note of encouragement below, and it would tell me to keep going, that y'all enjoy this stuff. My handle is The Math Hobbyist. You could drop a comment. Like, literally, that is the best way you can say thanks right now. Just drop a comment or share this stream and share this content with somebody who you think might enjoy it. These are ways that you can say thanks. You can comment, you can share with a friend or teacher, And if you really, really want to say thanks, absolutely no expectation, but you could buy me a coffee. Because I am unemployed, y'all, and I'm trying to see if we can make this a thing. I would love to do this for a living, if that were possible. I know it's going to take a long time to get there, but I hope we can get there. Thanks, the math hobbyist.com. Right now, this just redirects to buy me a coffee. Same thing, but this may change in the future. You know, maybe I go back to Patreon, or maybe I create my own bespoke platform. But thanks.themathhobbyist.com will always work if you just want to leave me a tip. So thank you for watching. Thanks, everybody. It's an absolute pleasure. My cat wants to say hello. Let's let her in. She wants to say bye to everybody who's still watching. Loon, you love mathematics? You love mathematics, Loon? You Loon? My Loon. Okay, thank you everybody for watching. This is a pleasure to hang out and do math with you all. I love mathematics very much, and I hope you do too. All right, bye. This was fun. Bye.